안녕하세요. 오늘 좋은 자리에 초대해 주셔서 감사합니다. 연세대학교 한준이라고 합니다. 반갑습니다. 오늘 강연은 영어로 발표를 진행하도록 하겠습니다. Okay, hello everyone. I'm really happy to be here with the wonderful audience here at Samsung Research. I myself was at one time part of Samsung. I used to be a software engineer at Samsung Electronics. My talk is titled Sensing the Future, Unveiling the Benefits of Sensing in Cyber Physical Security. And today I'm going to talk about very interesting, and I think it's a rather unique set of research that deals with sort of the intersection of sensing systems, mobile computing, as well as security. Today's talk, of course, the conference here is about security, so we'll try to focus more on this hacking. And specifically, I'd like to be talking a little bit about a relatively novel concept of what I like to call physical hacking. So we'll see what we mean by that. So before I begin my talk, I'd like to briefly introduce to you about myself as well as my research group. So I am currently at Yonsei University. I previously, prior to joining Yonsei, I was at the National University of Singapore. And prior to that was at CMU. And also, most importantly, my research group is titled Cyber Physical Systems and Security, in short, SciFi. My students, most importantly, of course, my students are based here at Yonsei, but I also have students and I remotely advise students back at Singapore. And so we, with my students, we work on this very exciting research topics that I'm going to be talking about today. So let's start my talk today. So specifically, computing has been dominant in the cyber world, right? We all know about online banking, Facebook, Gmail, and all of these things, all of which have been dominant in the cyber systems, right? But the computing is actually transforming, right? The paradigm of computing is now transforming into cyber physical domain, right? So we see the advent of self-driving cars, with the semi-autonomous systems, as well as eventually to fully autonomous systems, as our earlier speaker, Professor Hung Shin, has been talking about today, this morning, as well as smartphones and smart homes as well, right? All of which are now equipped with sensors and actuators to be, sensing and interacting with the physical world, right? So in light of this transformation, I'd like to pause for a minute and ask a very important question about security. Is the security that we have that we've been, all aware of in the traditional sense of security adequate and enough to cope with this transformation? And specifically, my answer to that is, of course, not, right? Because in the physical world, data rely much more on the physical relationships among parties rather than their identities alone. So let me try to give you an example of what I mean by that, right? So let's assume in the world of future, where we have, vehicles that are equipped with V2V communication, right? As we saw in the earlier talks. So let's say in this context, we have two cars driving on the road. Car M is driving in front of car A. And in this case, car M happens to be malicious. And car M, for whatever reason, wants to fool car A into believing that car M is actually behind car A and not in front of car A. So car M sends a message to car A saying, hey, car A, I'm actually behind you. Well, our poor little car A here has no choice but to really just accept this fact because there's no adequate way of verifying this locality information. Of course, in Korea, we have this dash cam, so maybe the visual information could help, but in many other parts of the world, this, there isn't really an adequate information. And one might think, of course, why can't we just simply, add GPS information and send and maybe sign this message, digitally sign this message and send it out. But unfortunately, digital signatures are great at verifying the identity, right? The digital identity, but it doesn't really prove the locality information, right? And GPS, of course, we know is very prone to spoofing attacks. So this sort of question encourages us to ask the following question, which is how do you actually verify and also bind together the identity and their physical relationships or physical context together? And the main question of this talk is, how can we teach these devices to reason and learn about their physical relationships and context, right? So this question has really, inspired us to think about how do you actually solve this question, right? And so we turn to what we know best, which is our physical environment and our, sort of physical world that we live in. And what we call is this notion of signals of opportunity, or really nothing but contextual cues like your speakers emitting sound like today, or dryers humming, or cars driving over potholes and whatnot, all of which can be captured by the sensors that are equipped in these IoT devices to eventually use this sense data to verify their physical relationships. And as a teaser, very interestingly, to the rest of my talk, is sometimes this traditional notion of noise can actually be used as very useful signals. And we'll see what we mean by that throughout my slides today, right? And taking this contextual information or signals of opportunity, what my students and I have been looking at is this notion of utilizing this context in the following two pillars. Specifically, how do you try to utilize these signals for security benefits, as well as novel attacks or physical hacking, right? So this is sort of like an ongoing research direction in my group, and also towards the later part of my talk today, if I have some time, I'll also glance over some of the additional direction as well. But in the first set of pillar, which is the security benefits, we've been publishing in the domain of secure authentication and physics-guided attack detection. And in the risks side of things, or physical hacking, we've been also looking at acoustic-based attacks or wireless-based attacks and attacks in smart home. And also in the additional directions, we've been looking into not specifically security problems per se, but it's quite related in healthcare, geolocation and mobility, metaverse and NFT, and accessibility for disabled. Right, so let's take a quick look. So today what I'll do is I will glance over on a high level, relatively, on some of these very interesting recent work of our group and try to sort of stir some discussions, hopefully towards the end of the talk, right? So as the first pillar, I'd like to go over some of our very recent security benefits sort of research in this context of IoT security, right? So we've been publishing in the top tier venues looking into the secure authentication aspects, but in terms of smart home or drones or semi-autonomous trucking, which is quite relevant to what Professor Kung-Shin has been presenting today this morning. But and we've also looked into physics-guided attack detection. And today I'm going to focus a little bit more on this sub-pillar, and specifically I'll cover a few, 2 or 3 projects on a very high level, and then I'll move on to the risks side of things. Right. So first, I'd like to talk about this counterfeit liquid detection that we presented at Mobisys last year. And so actually, this is quite interesting because we are witnessing a surge in the reported cases of counterfeit liquid food products, including alcohol, honey, and olive oil. And this you might have heard of a lot of news here locally in Korea as 가짜 양주, or or fake olive oils, or fake honey, for example. And you might think that this is relatively simple or not such a detrimental problem, but actually this is extremely detrimental because we've seen, as you can see from these articles, people actually die from drinking these fake liquor. Right? This is because a lot of the counterfeiters or the attackers actually mix very lethal substances like methanol and whatnot, right? But the problem with this is that it's actually really difficult for an average user to verify this. So let's just take a quick look at this counterfeit process, right? So we have this, let's say an olive oil. I never knew before working on this project, never knew that an olive oil could be so expensive. An expensive olive oil could cost over $700 US, right? And what the attackers would do is they would actually substitute a portion of this expensive olive oil with really cheap substitutes like peanut, soybean, or corn oil. They would adulterate it, mix it. But then what they would do at the end is they would factory seal this, right? So as an average user, let's say trying to purchase this over eBay or 당근 Market in Korea, for example, we would have no idea, right? And there's no adequate ways to verify this quickly. And for the attacker, this is very there's a lot of monetary incentive because these substances are much cheaper, right? So the main question of this part of this talk is how can we help the average users to detect this adulteration without opening the bottle, right? But only using commodity devices, right? So our work is as following. So let's say we have a user, and what the user would do is to simply flip out their phone, run our app that we've implemented, and just take certain video capture of this bottle, right? And what this app would do is locally it would automatically compute some function of this liquid properties, which I'll be talking about in a few slides. And eventually the app would be verifying or comparing the computed liquid properties against what's uploaded in the olive oil's manufacturer's cloud, right? And if that matches, then we have a pretty good idea that this content inside this bottle is authentic. If it doesn't, then we have a pretty good idea that this is probably a counterfeit. And what does that remind you of? That actually reminds you of software hash checksum verification, right? Hence our name of this project as Liquid Hash, right? So before advancing to a little bit more detail, let's take a quick look at the liquid properties, right? So there are 3 properties that we've been looking at, which is the density, viscosity, and surface tension, right? And all of these actually govern how these liquids would be behaving, right? And if we can calculate this liquid properties, then we can actually get to this notion of liquid authenticity. Unfortunately, however, from the smartphone cameras, you don't have sufficient information to actually calculate this liquid properties without opening the bottle, right? Because what the state of the art is, you would have to actually open the bottle, extract samples, send it to the lab, and then only calculate it with very expensive machines. But because we are limited by these 2 main constraints, namely the requirement of not being able to open the bottle, right? And also utilizing just normal, smartphone cameras, we have sort of a roadblocker. So my students and I have been really, thinking hard about it. But eventually what we were able to find out was that actually what caught our eyes was this bubbles, right? So actually, I don't have a bottle with me right now, but actually if you observe your bottle, you all have your water bottle today, right? You can actually see that there are these bubbles that form, and different liquids actually have different bubbles that arise. And so we were thinking, maybe we can do something very interesting with these bubbles. And what caught our eyes was that the bubbles actually have these characteristics that we defined, which are bubble size, shape, and speed, which actually can be observed by the smartphones. And we can actually, and these bubble characteristics, as we read a lot of this physics papers, actually, believe it or not, there are physicists that dedicate their life's work in studying bubbles only, right? So that's really astonishing, right? So we read these papers, and what we were able to find is that actually we can actually capture information of these bubble characteristics and eventually infer the liquid authenticity utilizing these bubble characteristics. So the high-level solution of liquid hash is the following, right? We would ask the user to flip the bottle without opening the bottle, and then we would capture that with our smartphone camera in a slow motion, right? Then you can get these bubbles, and then we would track these bubbles using computer vision techniques. So, of course, when I mention up until this point, it sounds really easy, but turns out that there are many technical challenges. Specifically, there are many noises due to human behaviors as well as noise due to liquid movements and etc. And so, for example, like noise due to, even if the same person flips this, it causes different patterns, etc. And also camera placement, like different distance and angles, as well as liquid movements. There are these regular, quote unquote, regular shaped bubbles as well as irregular. And also bubble trajectories are really noisy. Certain trajectories are erratic versus uniform. So we used a bunch of, and also another main concern was that, I guess the slide was lost in translation, but actually, essentially, there's really very minute differences between authentic liquid versus, let's say, counterfeit liquid that is mixed between 70% authentic olive oil and 30% sunflower oil. So all of these things actually add to different challenges, and so we had to design a sequence of signal processing pipeline as well as machine learning pipelines that actually deals with removing certain noises and then adequately differentiating these minute differences. Right? So I'm not going to bore you with all the details, but if you're interested, I'd invite you to read our paper on these pipelines. And also, let me just skip over the details. And so to evaluate our system, what we've done was we've bought a bunch of these different olive oil, honey, and vodka. Trying to buy vodka with research money was very interesting. And then also, so we've mixed these authentic liquids with different adulterants, such as peanut oil, sunflower, and etc. And what we also tested as baseline was to invite different participants to interact with the bottles, right? Some of which were authentic, some of which are adulterated, but they were not able. They were required not to open the bottle. And then we compared that with our results. And from our evaluation results, we demonstrated that liquid hash actually exhibited quite high detection accuracy, up to 95%, and it was robust against different parameters, such as camera to bottle distances, and it also generalizes across different adulterant concentrations and bottle dimensions. Right? Okay, so with and of course this was covered in different news articles, so I'd encourage you to read these news articles if you're interested as well. Okay. So with the interest of time, I'll quickly move on to the next work. And this work is also utilizing vision sensing with your smartphones, but slightly in a different manner. So actually, you might all be aware that these hidden cameras are a huge problem, right? In not just in Korea, but in worldwide issue, right? So what we have here is our police officers patrolling these public restrooms here in Korea, and they use these detector devices, what we call, to manually verify if there are hidden cameras or 몰카, right? 몰카 detection. And what these detectors are is it shines this bright lights, and it tries to look for any possible reflection. So here in this case on the left is the actual electrical socket, and there's a hidden camera inside it. And if you take a look at that with the detector, you can actually see this bright reflection. The problem is there are so many false positives, right? And the police officer manually has to verify this, right? So this is a huge concern. And what they've done is KBS actually made a documentary where they invited like 3 or 4 real police officers with these detector devices. And the documentary producers actually hid over 5 hidden cameras, and they gave them 30 minutes to find them. The police officers were not able to find every single hidden camera. So this actually is a huge problem. And the problem is, for average users, not even the police, right? For average users, this becomes even a more difficult problem, because how many of you actually carry these detectors, right? Do you have any, right, at home? No, right? So we were thinking, is there a possibility where we could actually just utilize everyday, device, which is our smartphone, right? And flip out our Samsung Galaxy phone, and it would be able to scan our environment, and the phone or the app that we make would be able to automatically detect and localize the hidden cameras. That would be really awesome, right? So let's say, so that's exactly our work here that was published at Census in 2021, where we actually utilize what we call this time of flight sensor, which is, actually, equipped in these devices to measure the distances of the objects for, augmented reality apps. And we sort of utilize the information to see if we can actually detect and localize the hidden cameras, right? So why this works is as following. So let's say we have an object without the hidden camera, right, here on the left side of the slide. If we, transmit this laser beam, what it produces is this is a diffuse reflection, which is quite weak in the amplitude, right? But if we have an object like this water bottle that has a hidden camera, and you shoot this laser beam, what it would produce is this what we call this retroreflection, which is a really strong reflection that reflects back. This is very synonymous to this cat eye effect that we are all familiar with, right? So this is exactly what we're using. So this is a sort of a screenshot of our demo video that you can look at from our online website. So if you sort of think that this bottle is suspicious, the user, we've implemented this, augmented reality app, and you can actually click on it, and you'd be able to scan, and the app would tell you, oh, here's a hidden camera, right? So you can take, and you can actually see that the hidden camera is shown here on the bottom right, right? So again, I'm not going to go into the details here, but this was, once we published this work, it was covered in various news articles. And I'm going to skip over this. And let me skip over to actually, I think I'll skip over this because of the interest of time. And now I'm going to switch gears to the physical hacking, or the risks of sensing, right? So what we also tried to do was to put on the attacker's, cap, and try to see if we can, come up with very novel, potential attacks that actually could eventually be introduced, so that we can help the community to defend against these before the actual attacks happen. Right. So I'm gonna go through a couple of recent work that we looked into. Specifically, we've looked into acoustics-based attacks. So we're trying to utilize sound, right, to see if we can actually extract hidden information for the attacker's benefit. Right? So in the first work, we've published this work in the Usenix Security Conference in 2021. We were trying to utilize, sound recording of a physical key that was inserted to a door lock to be able to reconstruct the physical key. Now, the problem is, when I first joined Yonsei a couple of years ago, and I was trying to explain this work to our students, I was really surprised that because most of Korean doors are digital door locks, the students, especially the undergrad students, have never used physical locks before. So I was super surprised. But hopefully, it looks like most of you have probably used physical locks here. So that's good. So as a quick reminder, for those of you who may not know how physical locks work, right? So we have this physical key, and the secret of the key, much like your digital door lock pin, is these cut depths, right? You have, in this specific case, it's 795,393, which is, it's cut 7 depth, and then 9 depth, and so on and so forth. And the the attacker model that we thought of here is a victim is trying to insert his or her key into the door lock to open, the victim's, office door, for instance. And as you insert the key, it makes this droop sound, right? And if we have an attacker that is walking nearby that door, the attacker could simply utilize the attacker's smartphone microphone to record the sound of this key insertion, and then later go back home, and as an offline attack, would be able to process this recording, and eventually would be able to reconstruct the key by deducing this secret, right? And from our extensive evaluation, we were able to find that in the best case, we could reduce the search space from 60,000 keys, right, of the key space, into just 2 keys, right, where one of the 2 keys would actually open the door. So what this means is that the attacker could 3D print the 2 keys and go back to that victim's door the next day, and one of the 2 keys would open, right? That's pretty crazy, right? And so that's exactly what we were looking at. And I hope the sound would work, but I guess the sound doesn't work, but this was just a sound recording of what it sounds like as you insert the key. And this is sort of the initial version of our experiments where we were failing quite a number of times, and we were trying to utilize, either microphones or vibration sensors and whatnot. And actually, my students is now a master at lockpicking, because we actually had to study how lockpicking actually works. Another issue was this key insertion speed, because even if we try to be consistent in inserting the key at a consistent speed, every trial is different per person, right? So we had to eventually make an algorithm that would be robust to this differing speed. However, in the very beginning, we wanted to sort of control that by utilizing a robot arm, because that was the most consistent thing. Of course, later, and that became our hot mobile paper initially, and then later we removed that assumption to make it more realistic by being robust against varying insertion speed, right? So, and then we made this door, and we utilized different microphones as well, and we were able to eventually get the evaluation results that I just mentioned to you. And again, upon publishing, we were covered by this communication of ACM News, as well as Forbes, and etc. Right? Okay. So next up, I'd like to introduce very briefly about yet another acoustics-based attack. Specifically, in this case, I think it's quite relevant to Samsung, because we've been looking into how your robot vacuum cleaners could be spying on your speech at home, right? So how many of you actually have robot vacuum cleaners? I think it's quite common, right? Unfortunately, I prepared a different brand. Sorry, I should have prepared a Samsung brand. But I guess it's not that good, because I'm trying to attack the device, right? So in this work, what we try to utilize is a way to actually exploit the LiDAR sensor that are equipped in these robot vacuum cleaners. So you can see that this circle thing on top of this robot vacuum cleaner is the LiDAR sensor, spinning LiDAR sensor, very much similar to the autonomous driving or cars that have this Velodyne sensors on top of their roof, right? What this does is nothing but a spinning TOF sensor, and it measures the it calculates the object's distance to the robot, right? And it's used for mapping purposes for the robot to go around and clean the house, right? But it turns out that what we were able to find is that the LiDAR sensor, essentially what a TOF sensor is you shoot the laser and it reflects off of the object, and you calculate the time, right? Hence the time of flight, and you measure the distance that way. But what we found is that actually it can actually, the reflection could actually carry a very minute speech signal that is induced by the victims nearby. So the tech scenario that we thought of was, and by the way, this was a time during COVID where work from home was, quite prevalent. And in this case, the victim engages in a Zoom call, let's say, and with the colleague of his, right? And the speech signals that are emitted from these computer speakers would minutely vibrate the objects nearby the computer. So for instance, the trash can, for example. And then what it would do is the lidar sensor that is equipped on the robot vacuum cleaner would emit the signal, and the signal would be reflected off of the trash can. But the interesting thing is that the reflection would now capture a very minute speech signal, like this 194706839, which is supposed to be the social security number. And that could be transmitted over remotely to the attacker. And through our careful processing, we would be able to capture certain information about the speech. Right? So here on the bottom right, we have our experiment set up, where we have the tweeters and subwoofers of the computer. And then the emitted sound would minutely vibrate the trash can, which is the target object. And then the robot vacuum cleaner would be able to capture that sound. Right? So here's sort of the capture of the actual sound being captured, raw lidar signal, right? That is capturing certain chirp signals like boom, 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 like that. And very interestingly, so not only that we were able to capture digits like social security numbers and your PIN numbers, but while we were writing this paper, it was in the midst of US presidential election. And we thought, what other interesting information other than your PIN numbers or digits would be privacy sensitive? And back then we thought, maybe inferring one's political orientation might also be quite interesting, especially because it was right before the US presidential election. So we thought, if we can understand, if we can know what news channel one is looking at or watching, person watching CNN News versus Fox would have very different political orientations. That would be quite interesting as well. So unfortunately, the sound doesn't work, I guess. But this is where we actually, it does work. So that is the introduction song of a news, right? And so what we captured was 20 different news articles or news intro songs, and we were able to classify different news channels, and eventually we would be able to understand the news channel that one was watching, right? And again, this was reported in various news articles, I'll move on. I guess I don't have too much time left. And we've also looked into wireless-based attacks to infer one's location or what videos you're streaming over your phone just by looking at the 5G channel, right, or 4G or 5G channel. And through that, we were able to secure this GSMA Mobile Security Hall of Fame, but I won't go into detail there. Right, so because I wanted to quickly discuss a little bit about the glimpse of my current research as well, right? So in my, so until now I've been showing you the security benefits and risks from the signals of opportunity, right, that these IoT devices can capture. But interestingly enough, we could also utilize these IoT devices, the signals that they capture through their sensors for various value-added services and sensing systems, right? Because the functionality and attacks, they have very fine line between them, right? And so we've been starting to branch out our research into various different applications, including healthcare, geolocation, and et cetera. So I'll talk about that a little bit. And in healthcare, we've been looking into utilizing wireless earbuds that Samsung also makes, and trying to utilize that for gait monitoring or chewing habit monitoring. And we've been also collaborating with Asan Hospital to measure or monitor remotely patients in the psychiatric wards. But I guess more related to Samsung would be this part, which is looking into geolocation and mobility aspects, which have quite, have similarities with the earlier talks today as well. So in the first part here, what we've looked into was ways to help these personal mobility devices, or try to localize these personal mobility devices that are quite prevalent, like Bird or Lime or Dareungi in Korea, for example, or these things, right? And the problem with that is GPS, especially in urban scenarios, like in Seoul, for example, is extremely noisy, and it's quite difficult to actually localize these personal mobility devices for the users because the GPS is quite off. So what we try to utilize is the road information, specifically the ramps on the sidewalks, to augment the noisy GPS information. That's what we've published at Hot Mobile, and we've received certain awards as well. And also another work that is in progress, which is quite relevant to security aspects, is trying to solve this fake driving detection. So what this is that Uber actually announced this quite an interesting and difficult problem that they are facing, which is trying to actually detect these fake driving attacks. What it is that an attacker would sign up as a legitimate driver and also sign up for various accounts of user devices, right? And without driving a single mile, what the attacker would do is to actually fake these rides by performing GPS spoofing. And so to Uber, it would look like there have been so many different rides that have actually happened with legitimate transactions, right? So why would an attacker do this, right? Because you would have to pay Uber a certain commission for each ride. So why would an attacker even try to do this? Well, it turns out that if you actually, as a driver or as a user, if you sort of utilize Uber and add up these driving miles, you would actually get back extensive rewards for being a loyal driver or loyal user, and that actually overcompensates the commission, right? So this has become a huge problem, not just for Uber, but various these ride-sharing services also this problem has been reported in China as well as in India, for example, right? So we're trying to utilize these road context information as well as other sensing modalities to be able to verify this sort of GPS spoofing attacks and fake driving scenarios. And I've submitted this proposal to Google, and we've been selected utilizing this sort of work, and we've been selected as Google Research Scholar to solve this problem this year as well. So I guess from today's talk, I wanted to go over on a high level of some of the interesting work that has been developed by my research group, specifically in the lines of security benefits, risks, as well as sensing systems. And I'd like to, I guess, conclude here, and I'll take questions. Okay, thank you.
네, 박수 부탁드립니다. 네, 교수님의 그 톡을 통해서 저희들이 센서로부터 여러 가지 얻는 이득도 있지만 이로 인해서 생각해봐야 될 위협도 적지 않다는 것들을 저희가 알 수 있었던 것 같습니다. 시간 관계상 질문 딱 한 분만 받아보도록 할 텐데요. 맨 앞에 여기 분께 마이크 부탁드립니다.
그 질문 드리고 싶은 게 그 연구를 조금 어떻게 시작하셨는지를 좀 알고 싶습니다. 그러니까 조금 발상이라든지 이런 게 좀 뭔가 그냥 일반적으로 떠올리기 쉽지 않은 것 같은 아이디어가 좀 많은 것 같아서 그런 게 좀 들어보고 싶습니다.
네, 굉장히 어려운 질문입니다. 사실 저희 연구실 우리 학생들도 여기 있는데 아이디어를 찾는 것이 굉장히 쉽지 않고 저희가 보통 활용하는 방법은 기존에 있는 뭐 논문들이나 이런 것들에서 새로운 그러니까 기존에 있는 어썸션들을 뺐을 때 새로운 어떤 문제들이 발생하고 그것을 통해서 새로운 연구 아이디어를 얻을 때도 있고요. 혹은 우리 그 아까 뭐 몰카 탐지라든지 이런 것들은 사실 뉴스나 이런 데서 사회 문제 해결 관련 그런 어프로치로 이렇게 새로운 아이디어를 또 얻는 그런 경우도 있는 것 같습니다. 근데 사실 항상 아이디어를 얻는 것이 굉장히 어려운 것 같습니다. 근데 그래도 예를 들면은 뭐 지금 제가 오늘 보여드린 것은 이제 몰카 탐지였는데 그것을 기반으로 또 새로운 워크가 이제 또 진행이 될 수 있거든요. 예를 들면은 지금은 사람이 자기 스마트폰을 가지고 뭐 공용 공간에 가서 이제 스캐닝을 하는 그런 방식이었다면 거기서 조금 더 새로운 문제들을 또 생각해 볼 수 있거든요. 파생되는 아이디어들이 있을 수 있죠. 예를 들면 만약에 이제 내가 개인이 아니라 뭐 빌딩 매니저라고 했을 때 이 건물 안에 화장실이 엄청나게 많잖아요. 그러면 이 기법을 가지고 여기에다가 조금 더 살을 보태서 예를 들면은 뭐 드론이 돌아다니면서 말이 될 수 있는지는 모르겠습니다. 이거는 저희가 좀 계속 고민하는 문제인데 화장실을 계속 스캐닝을 하면서 몰카가 있는지를 확인할 수도 있고, 그 다음에 지금 보여드린 것은 이제 히든 카메라 몰카였잖아요. 근데 사실 불법 촬영이라는 어떤 큰 주제 안에서 테크니컬하게는 히든 카메라, 스태틱 히든 카메라죠. 카메라가 움직이지 않는. 근데 요즘 뭐 뉴스를 보면은 지하철역에서 그런 것도 있잖아요. 그 몰래 촬영, 상대방을 몰래 촬영하는 도철이라고 하죠. 이런 것들은 사실 카메라가 움직이는, 테크니컬 관점에서 보면 카메라가 움직이는 거거든요. 그러면 완전 또 새로운 테크니컬 챌린지가 생길 수 있어요. 이게 그냥 겉으로 봤을 때는 그냥 뭐 불법 촬영, 몰카 이렇게 생각할 수 있지만 그 테크니컬한 문제를 보면은 완전 다른 또 문제가 파생이 되기 때문에 계속 여기 하나하나 빌드업을 하면서 이렇게 새로운 연구를 진행을 하는 방법을 취하고 있습니다.
네, 답변 감사합니다. 다시 한번 좋은 강연해 주신 한준 교수님께 박수 부탁드립니다.